Okay, so since the beginning of this semester, we treat the material too hard. What we have done earlier, we melted the material. We shape it in the mold, right? Is that enough? No. We did some deformation on it. We did the rolling, we did the extrusion, withdraw. What else? Punching, shearing. Is that enough? Now, usually it's very rare to use the material after these two operations. We still need to do something, and that's what you had, for example, in the engine block example you had. Okay, you casted the material, and now you have to do something else to make it ready to be used. Now, the same thing if you, for example, going to manufacture the crank for the same engine. You casted the one, you have some time to improve the property by doing some forging, like we had last week. But still, you have to have a good surface finishing to ensure less friction between the moving parts. So we are going to have another operation today to be covered is at the solidification process, which is the melting and casting. Particular process we are going to talk about this one later in the powder metrology. Deformation process, forging, rolling, and the other processes. We have to do some material removal to have the final shape with the accurate dimensions and specification, of course. Also, we have two classes of the assembly, which will be the mechanical assembly and the joining, and we're going to have a lecture for that. So what we are going to talk about today is the material removing process. We have to shape the part by removing some of the material to take it to the designed shape, design specifications, and having a good surface finishing. So it's a shaping operation based on the removal of the material from the original work part. So the remaining part has the final geometry. And of course, as I told you, the specification. We can do that by simply the machining process. And that's what you did upstairs. You use the disc lathe machine to remove some of the material to have the final shape. Also, have you did some tapping? Make the internal thread. Okay, now I just remove material to have the final shape. So we can do that by doing the turning, milling, and drilling. Even in drilling, actually, I remove material to make a hole. I can do another process like the reaming and boring. We also can do it using the abrasive processes. Now, in this case, we're not going to remove the material as a chip. We're going to remove it as a powder shape. Okay, so a material removal by hard abrasive particle, like the grinding process. Also, we have some non-traditional processes by using different type of energy to perform the cutting process or the material removing process. So that's a chart which can show you what are the material removal processes we have: conventional, which is the machining, abrasive processes, and non-traditional machining. So that's the machining process. We have a cutting tool, and the material is going to be removed as a chip form. These are the standards of the machining process. So we are going to have the cutting tool. We are going to have rake face. Remove a layer. We are going to have a new surface. This layer will be removed by a certain thickness, which we call the depth of cut. So machining is a broad term used for describe the removed material from the workpiece. Cutting generally involving a single point or a multiple cutting tools in the case of the milling process or the drilling process, each with a clearly defined geometry. The cutting action involves the shear deformation. So actually what we have here is a shear deformation for the material from its original piece. The shear deformation of the work material to form a chip, and that's what we have flying here. As the chip is going to be removed, a new surface is going to be exposed. We can have the rake angle as the positive rake angle if it's going to go toward this side, or it can be a negative rake angle. We're going to learn about why we have the rake angle while we do some calculation on the operation of the cutting. So The machining will verify the work material can be machined. We are going to most frequently is going to apply for the metals. It can be done for the plastic, but usually it's going to be done for the metals. Variety of the part shapes and special geometry features possible, such as we can do the screw through. Okay, and this is not for the bolt and nuts. We're talking about bigger size. Accurate round holes. We can have very straight edges and flat surfaces. And good dimensional accuracy and good surface finishing. These are the good points we can have for the machining process. Still, we're going to waste material because we're going to do some machining, remove the chip, and usually these chips are not going to be recycled because it's going to be contaminated with the coolant fluid. Time consuming. You remember that in the case of the casting, we melt the material, we put it in the mold, solidify, we took the part out. Sometime we are going to have the net shape part. That means we can use it directly. Now, it's very rare to have machining on the plastic part which has been casted, because even the thread can be done by the injection molding. Okay, the operation we can have, there's something at the top, yeah. So anyway, the most important machining operations we can have are the turning, the drilling, and the milling. The principal changes between that is about which axis is going to move and which axis we are going to feed the cutting direction onto. Other machining operations possible are the shaping and the planning, the broaching, and the sewing. We're going to cover the whole 6 things today. So classification of the machine part can be a rotational part, symmetrical one, and this can be done on the lathe machine because the part is going to rotate symmetrical. We're not going to have any vibration due to the uniformity of the shape. Also, we can have it as non-rotational, like the block-like or the plate-like, and this can be done on the milling machine. When the part is going to be fixed, the cutting tool is going to rotate. I did upload this one, right? It's available online. Okay, so we have other 2 classifications which are either generating or forming. If I'm going to do the cutting by the feed route of the cutting tool, like this cutting tool, for example, is going to move in straight line, I'm going to have straight shape. If I'm going to move it in taper line, I'm going to have taper cutting. Contour path, I'm going to have contour cutting. Same thing for the plane milling, moving this direction, just get a flat surface. Or even for the profile milling. So the shape, the profile of the final shape is going to be decided by the moving path of the cutting tool. But if I'm going to do the forming, the cutting tool shape will be cut out on the surface of the material, and I'm going to have the final shape, which is a duplicate of the cutting tool shape. And that's what I have in the form turning. In the drilling, the whole diameter and shape will be the same diameter and the shape of the cutting tool. And in the case of the broaching. Okay, sometimes we can mix between both. Now, this cutting tool wedge is going to be the same as the thread shape, but it's going to move in a path. So it's mixing between the generating and the forming at the same time. The same thing if I'm going to have the slot generator and the T-slot milling cutter. So actually what I'm going to have at the end is the shape of the slot cutter, but it's going to be moving in a path. So it's mixing between the forming and the generating at the same time. Now for the cut itself, it can be divided into rough cutting and the finishing cuts. At the beginning, if I'm going to have a block, for example, which have the thickness of, let's say, 200 millimeters, and I would like to have the surface, the next surface, to become something about 180 only, I have to remove 20 millimeters in thickness. Usually, for most of the material, even the aluminum, you cannot cut the 20 millimeter in one shot. So you have to divide it into cuts, multiple cuts. So the first cuts, I would like to go from the 200 to 180. I'm not going to go to the 180 in one shot, as we said earlier. Maybe I'm going to divide it into 4 millimeters each time. Each time I'm going to remove 4 millimeters until I'm going to reach the final 4 millimeters. When I'm going to do the rough cutting, deep thickness, fast feed rating, then I'm going to have rough surface through the cutting. The final surface should be smooth. So the last 4 millimeter, I'm going to divide it, for example, to 3 millimeters in one shot. And the last cut is going to be the surface finishing cutting. I'm going to cut 1 millimeter with more higher velocity and less feed rate. And same thing, of course, for the turning. You can do the rough cutting very fast, then the last cut is going to be finished cutting, is going to be more uniform. So the roughing is remove a large amount of the material from the starting work part. Some material remains for the finishing cutting, as this will be last a very thin layer till the end. We're going to have high feed and depth, but we're going to have low speed of cutting. For the finishing, is going to complete the part geometry with good surface finishing. The last layer we left, the thin layer, can be decide what will be the final dimensions, the tolerances, and the finishing we're going to have. So we're going to use low feeds and depth of cut, but we're going to have very high cutting, higher cutting speeds for the finished cutting. I'm going to show you a video for that later. You can see the example of doing the roughing very fast. That's the last one. The feed rate is going to be slower, but the velocity of the part is going to rotate faster. Now, the cutting tool classifications, we can use the single tip cutting tools, just single contact, and we try to reduce the contact as much as we can. That's what happened. But in the case of the turning, usually we're going to use what we call the single point cutting tool. We're starting from this point. We start to have the shearing on this side, forming the chip, and do the cut. So one dominated cutting edge, the point is usually going to be rounded to form the nose radius. The turning uses the single point tools. In the case of the milling, multiple cutting edge tools. So each one is going to do its part while we do the feeding. Actually, the feeding is going to be to the right direction, start to remove the material from the face. More than one cutting edge, motion relative to the work achieved by rotating. The drilling and the milling use the rotating multiple cutting edges tool. What we have during the cutting is actually what we have at this shape. Now, what we're doing is we're pushing the cutting tool toward the material. We start to have the shearing force in this surface. And obviously, you can see that the thickness, the original thickness of the cut, which is the depth of cut, is going to be less than that, the final thickness of the chip. So the equation we have for the chip thickness ratio is the following. The R is equal to the thickness of the original chip divided by the final thickness of the chip, TC. Because we said that the TO is always less than the TF or the TC, we're going to have this value is always going to be less than 1. You may have an example for this one on UTS online. Try to use these equations later to find the solution. Now, okay, now this is the chip thickness ratio, is the original thickness of the chip divided by the chip. Yeah, sorry.
Why do you need to know? Why is it important to know the thickness of the chip you're cutting off? Isn't that what you're discarding?
Well, you will see how we can use this one. Because actually, if you need to calculate what the force you need to do the cut, you should start from here. Okay, so once again, this is the chip ratio, and it's always less than 1. Now, to find the shear plane angle, you're going to use the R value and the rake angle value on the cutting tool. I need to find what the shear plane angle, because this will help me later to decide how to do best cutting with less force, because less force means less power. Okay, so the tangent of the phi, which is the plane angle value, is the R multiplied by the cosine of the alpha, which is the rake angle that we decide during the cutting, divided by 1 minus the R multiplied by the sine of the alpha. Also, the shear strain value you are going to generate in this area can be calculated by using the following equation. Gamma is equal to the tangent of the phi the one we calculate using the R, minus the alpha value, which is the rake angle value we decide on the cutting tool, plus the cotangent of phi. Now you can see what the need of the chip ratio. Okay, now the chip actual formation is going to be something like that. It's not only the shear deformation zone. Also, we're going to have tertiary deformation zone on this side, and we're going to have secondary deformation zone on the contact area between the cutting tool and the chip. So this will be the more realistic shape. We can divide this one to a triangular shape, so it's going to be much easier to be analyzed. Type of the chip in the machine we can have is this continuous chip, and that's what we saw in the video. This usually going to be done in the brittle work material. Low cutting speed, large feed and depth of cut, and high tool chip friction. Again, to have this continuous chip. Sometimes this is preferable. Sometimes, not all the times. We can have the continuous chip. This is in the ductile work material. Like, for example, now give me an example between the ductile material and the brittle material. Aluminium and ceramics. So the video we saw for the this continuous chip was for the aluminium. Okay, if I'm going to cut the steel, it's going to be ductile work material. Usually we're going to have continuous chip. High cutting speed, small feed and depth, sharp cutting edge is one of the most important things, and the low tool to chip fraction. So usually if I'm going to use a new cutting new cutting tool, you will see that at the beginning it starts to do very nice continuous chip during the operation of the machining. When the wedge is going to get weird, you will see that the chip is going to be discontinuous, and this is one of the signs tell you either to change the tool or sharpen it. Still, we may have built up edge. Okay, and this built up edge is actually melted material, which is going to be solidified later, and we get the particle on the new surface, and this is not desired. So the continuous chip would be UE, the built up edge. This happened in the ductile material. We are going to have low to medium cutting speed. The tool chip fraction causes the portion of the chip adhere to the rake faces here, and we are going to have the BUE to be formed and breaks off cyclically, as we can see here. And we have the serrated chips, which is the semi-continuous with the sawtooth appearance, as you can see here. The cyclic chips form with the alternating of the high shear strain we are going to have in this place, and then we are going to have low shear strain when we are going to remove after. Associated with difficult to machine metals like the at the high cutting speeds. Like, for example, if I'm going to have the special alloys, very hard material, so we're going to have very high strain, then we're going to reduce the strain later, so we're going to have this shape of the chip. The force acting on the chip during the cutting process. So this is the shear plane. This is the tool. So we're always going to have forces and forces reacted against this one. So we had the friction force, the F, and the normal force to the friction force, N. On the other side, we have the shear force and the normal force to the shear force. The resultant should be equal but opposite in direction. The resultant vector addition of the N, F and N, and the R prime is the vector addition of the Fs and Fn. So the force acting on the chip must be in balance, so the R prime should be equal in magnitude to the R, but should be opposite in direction. R prime must be collinear with the R value. The coefficient of friction and the shear stresses, that very important thing, because we are going to have direct contact between two hard material while doing the cutting. Friction will cause the heat, so that's why we have to understand how we can get the coefficient of friction between the tool and the chip. So coefficient of friction of the tool and chip is equal to the force we are going to use divided by this normal force. So the shear force divided by the normal force will give you the value of the mu. The friction angle related to coefficient of friction is going to be tangent beta is equal to the mu. That means that the beta is equal to the tangent inverse of the mu value. The shear stress tau is shear stress of the S of the work material during the cutting. And this can be calculated by using the shearing force on the chip divided by the area of the shear. The AS is the area of the shear plane, and it can be calculated by using the original thickness of the chip multiplied by the width of the chip divided by the sine phi. The sine phi one we calculated by using the R value. So actually I'm passing this one fast because we're not going to have a calculation example today. Okay, you can use these equations later. You can read the example you have in the book because I'm not sure if you're going to have something similar to this one in the final exam now. Okay, so the cutting forces and thrust forces can be calculated. We said that the forces Fn and Fs and Fn cannot be directly measured. It's impossible to put any measurement tool in this point to calculate what are these forces are. But other forces acting on the tool, like the cutting force, this cutting force, because we can check what the resistance we have on the tool, and the thrust force, the Ft, can be measured. So we measure these two values only. Then from there, we can use these two values to calculate the value of the Fn, Fs, and the Fn by using these equations. Okay, so you can see that always going to involve the cutting force and the thrust force to calculate the value for the Fn, Fs, and the Fn. Actually, I led the student doing that in another subject, not here. The shear plane angle, phi, is equal to 45 degree plus alpha divided by 2 minus beta divided by 2. Okay, so the shear plane angle phi value is going to minimize the energy required for the cutting process. That means I would like to have lower value for phi, which is going to give you less forces of cutting. So Merchant found this equation. How can I reduce the value of the phi? What am I supposed to change to reduce it? Which value, if it's an increase, going to reduce the value of the phi? Which one is going to increase the value of the phi? You can see we have plus, we have minus. If I'm going to increase beta value, I'll reduce the phi value. If I'm going to increase the alpha value, which is the rake angle, something I can control, I can simply increase the phi value. So higher shear plane angle means a smaller shear plane, which means lower shear forces, cutting forces, power, and the temperature. So I always try to increase the value of the phi by increase the rake angle and reduce the beta value. So I highlighted this one because it was a question. I remember this question. How we can simply change the value of the shear plane angle. And how will that going to affect the cutting process? It's page 20. Just write down the page number, and small details better than writing down everything. Okay, so to increase the shear plane angle, I can increase the rake angle alpha, something I can control, reduce the friction angle, or reduce coefficient of friction beta. We saw how we can calculate the beta value, changing actually the force divided by the force n, which give you the mu value, and this will simply change the value of the beta. So the power and the energy relationship we have in the cutting. The machining operation requires power, of course, and this power will go to the motor will go to the gearbox, and the gearbox will translate it to the chuck, for example. So the power performed machining can be computed by using the equation. The power of the cutting is equal to the force of the cutting multiplied by V, which is the velocity of the cutting speed. Okay, so I always try to make this one lower value. Sometimes I need a high speed cutting, but I have to control the value of the FC in this case. The cutting temperature is one of the important things we have during the cutting. So something about 98% of the energy in the machining is going to be converted into a heat, and only 20% is going to retain as the elastic energy in the chip, because you can see that the chip is concave. That's where I'm going to have elastic energy on it, but this is only 2%. 98% is going to be a heat. This can cause temperature to be very high at the tool tip. And actually, you saw most of the example. You can see actually there's a smoke generated. We did what we call the dry cutting, because this is what we call the demo cutting. We just want to show you what's going on. We usually try to prevent that by using something we are going to talk about at the end, which is called the cooling fluid. So high cutting temperature at disadvantages are, we are going to reduce the tool life, produce a hot chips that pose safety hazard to the machine operator, and one of the most important things, we are going to cause inaccuracies in the part dimension due to the thermal expansion of the work material. High fraction, high temperature generated, the part will be expanded. I did the dimension of the cutting according to my design. I leave it to cool down, it's shrinked. So we can use analytical method driven by Cook to check what will be the temperature generated during the cutting process. So the temperature is equal to 0.4 U divided by the rho C multiplied by the velocity original thickness divided by K out to power 1/3. T is temperature raise in the tool interface. So this is delta T. If we start at 25, this will be added to the 25 degree. U is specific energy for the material and the cutting tool. V is the cutting speed. TO is the chip thickness before the cut. The rho C is the volumetric specific heat of the work material, and the K is the thermal diffusivity of the work material. Direct measurement experimental method can be used to measure the temperature on the machining simply by putting a tool chip thermocouple. This will give me what the temperature we have on the chip. Kinnetrigger found a speed temperature relationship. Obviously, if we're going to have higher velocity, we're going to have higher temperature to be generated. So trigger equation tell you that the temperature is equal to the K multiplied by the velocity up to power M. Okay, so the T is the measured tool chip interface temperature, and the V is the cutting speed. So the following diagram, I think, sorry, that's one of the example we had if we are going to have a dry machining process. Okay, can you tell me why they're doing that? Why they're doing that? Exactly, it's for testing. Okay, we finished with that, right? I think I need to, yeah. So the other parameters we have in the machining are the cutting speed, V. Well, I think I missed something, because I remember there's a diagram showing you the relationship between the velocity and the temperature. I think I either removed those to come later. So the parameter we do calculate during the machining process are the cutting speed. We can change the cutting speed. The feed rate value, how many meter per second we're going to move the cutting tool to do the cutting. This is secondary motion, and the turning process is going to be, sorry, this is the speed, primary speed is going to be meter in second. The feed rate is going to be how many millimeter we're going to have per revolution of the part in the case of the milling machine, turning machine. In the milling machine, how many millimeter per tooth we're going to feed the cutting tool. The depth of cut is how much you are going to penetrate the tool below the original work surface. Single parameter, and it's going to be in millimeter. Is going to be the depth of cut we are going to have. The resulting material removal rate, which is very important. How much cubic millimeter of the material are going to remove each second. Okay, and this can be calculated by multiply the V value by the feed value by the depth of cut. Okay, now the thing is that it's not going to be actually this feed. We have to change this feed to a linear feed value, and this will depend on the value of the RPM we're going to have either for the part or the cutting tool. Because this one is in millimeter per revolution, we have to multiply it by the revolution per minute and change it to a linear value. So the turning parameters illustrated, as you can see here, as the part is going to rotate, is going to have the RPM value. This value, the F, is going to be the feed rate. This is the depth of cut, and this is the velocity we're talking about, the cutting speed. Actually, if we're going to take an imaginary point on this surface, the speed of this surface as a linear value is going to be the V value. In the case of the milling, okay, this is the depth of cut, how much we are going to penetrate the cutting tool inside the surface. It's either going to be the feed direction where the part is going to move in this direction, and we are going to have the velocity going to be straight on the cutter itself. In the drilling, we have one axis of rotation and one axis of movement. So this will be the feed direction. The RPM will be around the same axis, and we are going to generate the hole in the part. So for machine operation parameters are in the turning process, we have the workpiece rotate, and we are going to have a single point cutting tool. The speed is going to be the surface speed of the workpiece because the workpiece is rotate. The feed is going to be parallel to the workpiece axis, this direction. Depth of cut is going to be the tool penetration below the original work surface as usual. In the drilling process, the tool is going to rotate. The single pass cutting we're going to have. The surface speed is going to be of the tool itself because the tool is rotate. The parallel to the axis of the rotation, because we have one axis as well, is going to go up and down. The depth of cut is going to be penetration of the tool below the original work surface. The milling process, the tool will rotate, multi-point cutting tool, and we're going to have the surface speed on the tool once again because it's rotating part perpendicular to the tool axis. We're going in this direction for the feed, this rotation, and this is the feed direction, so it's going to be perpendicular to it. And once again, depth of cut is going to be tool penetration below the original work surface. For the rough and finish cutting, we have standard values. For the roughing, always the number of the passes is going to be more than 1. We said once again, if we would like to cut 20 millimeter depth, we are going to divide minimum to 4 multiplied by 4. 4 cuts. Each time we are going to remove 4 millimeters. We finish the rough cutting. We had extra 4 millimeters. We are going to do the finishing to achieve the final dimensions and the tolerances. So we are going to limit it to 1 to 2 maximum passes. The speed is going to be low in the case of the roughing, high in the case of the finishing. The feed rate is going to be high in the roughing and low in the finishing. Depth of cut is going to be high in the roughing, low in the finishing. Now, for these values, these are the averages. We can go lower, but you cannot go higher. Remember to use this table when you are going to do the major project for the gear pump, because you need to do some calculation for the roughing and the cutting. Now, turning operation, once again, we're going to use a single point cutting tool to remove the material from the rotating workpiece to generate a rotationally asymmetrical shape. The machine is called the lathe machine. We can do all these types of the cutting, like facing, like this, where it's facing. I can see it here. Well, facing is not here, but actually facing just remove a layer from the face of the part. The counter cutting, like this one. The chamfering, the parting, which is the cutting off of the part, and we can do the threading on it. And that's what's happening actually in the turning machine. This is the engine lathe. This is not the numerical control one. I actually have a gearbox and you have to change the speed. We're going to pull the part in the spindle by using the chuck. This will be the tool post. The tool is going to be fixed here on the chuck. And we can use the tailstock if we're going to have long part to support it from the end. So method of the holding of the workpiece in the lathe is the chuck. We can hold the part between the centers by using the tailstock. We can use the collet. The collet, when you press a button, is going to be open. When you release it, it's going to close. And we can use the face plate. If I'm not going to have a symmetric, well, I'm not going to do the profiling from the outside. For example, a square shape, I can fix it here and do the internal cutting for the part. The turning lathe, the one which have multiple cutting tools at the same time. And this cutting tool can be changed either by pulling a lever or simply is going to be done during the programming process. So the turret lathe is manual operation is going to be replaced by the turret that hold multiple tools at the same times. These tools are going to be rapidly brought to the action by the indexing of the turret. The tool post is replaced by the multi-sided turret to index the multiple tools at the same time. The application is going to be high production work that requires the sequence of the cuts of the parts. I'm not going to stop it and change the tool. Simply is going to be indexed. It's going to change according to the program I'm going to have for multiple cuts on the work part. We have the chucking machine, which uses a chuck and is a spindle to hold the part. So this actually doesn't have to be indexed as the chuck process. You know, the chuck, we have to open that, take all the jaws away, and put the part. In the case of the chucking machine, is going to be done electronically. No tailstock, so the parts cannot be mounted between the centers. The cutting tool action is going to be controlled automatically as well. You can see that this one is actually a turret. The operator job is only going to be the load and the unload of the part. Application is going to be short, lightweight parts. The bar machine, if I'm going to do continuous cutting for the bar parts, I do the work, cut and feed the part once again, which is going to be usually a part of a bar, long bars. So I have what we call the bar feeder machine. If you check any lathe machine, even the small one we have upstairs, where I can find a hole at the end of the machine, which take you through the chuck to the cutting area. So this one is similar to the chucking machine, except that the collets replace the chuck, permitting the long bar stalk to be fed through the head stalk from the end. At the end of the machining cycle, the cut-off operation is going to be separate the new part, highly automated computer numerical control, and the application is the high production of the rotational part. And that's why we are going to use this machine in the gear pump project to cut the shaft gear. We have the automatic screw machine, which same as the automatic bar machine, but smaller. The diameter of the bar is going to be smaller, and this one is going to be used to high production of the screw and similar small hardware items. We have the multiple spindle bar machine. You can see that we have multiple spindles, and on each spindle we are going to have one of the operations. So we can do multiple operation symmetrically. You can see that we have operation 1 here, operation 2 here. So it's going to rotate, do, for example, 6 operations. Then we're going to have the finished part ready in one setup. The tracer lathe is an old format of the CNC. Actually, it's duplication process. So you can see that we have cam follower here. You can have a small cam follower in this place. It's following this profile, and it's going to move the tool post forward and backward according to the shape we have here. So the cutting tool is going to have the tool cut path the same as this one, and that's what we're going to have. This one is one of the old form of the reverse engineering. So the lathe has the ability to follow the template to copy the shape of the contour on the work part. The boring process is actually a turning process, but instead of working on the outside diameter, we're going to work on the inside diameter. The most important thing is that we're not going to generate the hole. We're just enlarging this hole. So the difference between the boring and the turning is that the boring performed on the inside diameter of the existing hole. It should be existent. It's not going to be drilling. Turning is going to be performed on the outside diameter of the existing cylinder. In effect, the boring is going to be internal turning operation. The boring machine is different, and that's what we can see for the engine block, and you can write down that in your project. Horizontal or vertical refers to the orientation of the axis of the rotation of the machine spindle. This one is vertical. The cutting operation in the drilling, now instead of we are going to have a single edge, we are going to have minimum 2 edges, and that's what we are going to have there. So create a round hole in the work part, construct with the boring, which is only going to enlarge the existing hole. This one is to create the hole. The cutting tool is going to be called the drill or the drill bit. Construction performed on the drill press, the one, but you also can be done on the vertical mill or on the lathe machine also. This one is actually on the lathe machine. Don't do that. Now, we can have 2 types of the holes, which is the through hole and the blind hole. If I'm going to do the drilling, to pass to the other side of the work part is going to be a through hole. And I think you learned that in the SolidWorks. The blind hole, if I only going to drill it to a certain depth. We also have some calculation to calculate the force required to do the cutting on the drilling. I'm not going to talk about it today. So we will go to the reaming process. I did the drilling, but I want to enlarge it with good surface finishing to have higher accuracy. So I'm going to use the reaming process with slightly enlarge the hole to provide a better tolerances on the diameter and improve the surface finishing. That's the reaming process. Just remove very thin layer from the hole to get the exact diameter with good surface finishing. The tapping process is the process of generating the thread to the inside the hole. So used to provide internal screw thread on existing hole, and the tool is going to be called the tap. The counter boring provide a stepped hole. So instead of having one hole level, we're going to have 1, 2 diameters. Same thing in the other side. So the more operation we can have is the counter sinking. We can have the center drilling. We can have the sport facing. To accurate hole making, you have to follow the following steps. First, you have to do the pilot, which is of the center drill. That's the process when you actually put the drill on the center point of the desired hole. You don't start anything, just put it there. Okay, now this is my center again to drill. Then you do the drilling operation. Then you do the boring if you want to enlarge it. Then you do the reaming process. And later you do the tapping if you're required to have a thread inside. This is the drill press. How to hold it on the part on the drill press, either using the vise, fixture, or the drill jig. The milling operation. Now we are going to have multiple cutting edges and multiple axes. So it's mixing between the process of the milling and the process of the drilling. So the machining operation in which the work is going to feed past rotating a tool with the multiple cutting edges. The axis of the tool rotation is going to be perpendicular to the feed, as we said earlier. The cutting tool is called the milling cutter. The cutting edge is called the teeth. The machine is going to be called the milling machine. And interrupted cutting operation. The basic milling operation is create a planar surfaces. Just make a planar surfaces. But we can do multiple geometries now because we have the numerical control system. We have two basic forms of the milling, which is the peripheral milling or the face milling. Now, the cutter axis is going to be parallel to the surface has been machined. So you can see this is the axis and is going to be parallel to it. Cutting edge is on the outside of the peripheral cutting. That's the peripheral milling. For the face milling, the cutter axis is going to be perpendicular to the surface being machined, and the cutting edges on both end of the outside of the peripheral cutting, as you can see here. So the main difference between them is going to be what will be the position of the axis of the rotation. It either is going to be cutter axis going to be parallel to the surface, or is going to be perpendicular to the surface has been machined. The peripheral milling types we can have is either the slab milling, where it's going to be wider than the work's face. We can have the slotting process, the side milling. We can have the straddle milling on both sides, and we can have the form milling because the shape of the cut is going to be copying the shape of the cutting tool, so it's going to be a forming. The types of the face milling, we can have conventional face milling. Now, once again, you can see that we again cut a new surface, and not for shaping, so it's going to be something similar to that. The cutting tool diameter is wider than the width of the cutting part. We can have the partial face milling. We can have the end milling. We can have the profile milling when we are going to cut on the sides, not on the top. And we can have the pocket milling when we generate a pocket inside the part. And we can do the surface contour. Now, if you can see that this one is a flat head and this one is rounded head to do the cutting of the contour. So now what's that operation is? It's a face milling, but which cutting we're using? To remember this one. It's either peripheral or the face milling. The axis is perpendicular to the surface. So it's face milling. Okay, and what do I going to have here? He's doing the pocketing process. Contour cutting. No, this is profile. Once again, yeah, it's going to be pocketing process. But he did the profile on the other side. Okay, now the classification of the milling machine, we're going to have either is going to be horizontal or vertical knee and column milling machine. The horizontal, we're going to have the cutting tool to be rotate horizontally. Vertical that means going to rotate vertically. Now you can see that we have some axes here, X, Y, and Z. In the milling machine, the rotation axis is always going to be the Z. The longest side of the table is always going to be the X. And any third axis is going to be the Y. So in the case of the vertical, that's the Z, the vertical one. The X is the longest side of the table, and the other one, the shortest side of the table, is going to be the Y. In the case of the horizontal, this will be the Z axis, the horizontal axis, and longest side is going to be the X axis, and the last one is going to be the Y axis. I'm sorry, the Y, that's wrong. I found something wrong in the book. This is the Y, this is the Z. Now, the machining center is more advanced machine, highly automated machine tool that can perform multiple machining operation under the CNC control in one setup with minimum human attention. So typical operation is going to be the milling and drilling at the same time. We can have 3, 4, or 5 axes. The 3 is the basic one. We can add another axis by making the table to be moved in angles. Other features, automatic tool changing, the pallet shuttle like this one, so we can work on this pallet. When we finish with this part, this pallet shuttle will rotate, start working on the other part at the same time. And we can have the automatic work part positioning. The mill turn centers is mixing between the turning and the milling. So you can see that the part will start to rotate. We perform the turning operation. Then we can stop it, change the cutting tool, and start to work on it as a milling operation. I hope I have video for that. So highly automatic machine tool that can perform the turning, milling, and drilling operations in one setup. The general configuration of the turning center is the mill turning operations. Okay, I'll leave this one because I hope that I have the video on the other side. Yes, that's the video. Okay, so we fixed the part. Because actually this is a bar machine. I show you how the part is going to be fed from the end. Actually, it's fed from inside, and we have the stubber to decide what will be the length. So first we start to do the turning process. The part is rotated, the cutting tool is stationary, moving to do the feed cutting. Okay, now it's fixed. The cutting tool is rotating. So that's the milling process. And we can do the drilling as well. Okay, so that's the tapping process to generate the thread. Anyway, I have to pass this one. The other operation we can have is the shaping or the planning. Actually, the same process. The only difference is that we either going to fix the cutting tool, move the part, or move the part, fix the cutting tool. The only operation we are going to have, we are going to remove a layer line by line. So this one is the shaping, fixed work part. The cutting tool is going forward and backward. The feed direction is going to be in this, the feed direction in this one. The depth of cut is going to be in this direction. And the other part, which is the planning, we're going to have the fixed tool cutting tool. The work part is going to be feed against the cutting tool. So a straight flat surface is going to be created in the both operations. Interrupted cutting operation, the subject tool is going to impact the loading when it's going to entering the work part. Typical tooling is going to be a single point at high speed steel tool. Low cutting speed due to the start and stop motion. So this will be the shaper and this will be the planner. Okay, so this one is work table is fixed and the cutting tool going forward and backward. And it can move in this direction to do the depth of cut. In the case of the planner, the cutting tool is going to move in the depth of cut direction only, but it's not going to move forward and backward. The table will move forward and backward, something similar to the case of the grinding process. The projection operation, we're going to have a multiple teeth cutting tool once again. Each one have a different height. So a multiple tooth cutting is moved linearly to relative work direction of the tool axis. Advantage, we are going to have good surface finishing, close tolerances, variety of the work shape possible. Cutting tool is called the approach, and it's always complicated. That's why it's quite expensive. Actually, that's the shape. This is just the cross side. So what's happened is, as I'm going to feed the cutting tool inside the work part, start to remove the first layer, the second layer, the fourth layer, the fifth layer to get the dimension I would like to have. That's very thin depth of cut. That will make it very good surface finishing because each time we're doing a finishing cut, but multiple layers. So actually a single pass will generate the cut you can have on the side. This is very useful method if you would like to make a keyway on your, for example, the gear. You're always going to have a keyway, so you can simply pass the approaching cutting tool in one pass, and you are going to have the shape to be generated. So this is the external type of the approaching, and we have the internal types of the approaching. The cutting operation by using the sewing is a very simple thing. We are going to have multiple teeth. In one move, going to remove a layer until we are going to separate the two parts. So cuts a narrow slit in the work by the tool consisting of a series of narrowly spaced teeth. It's called the saw blade. Typical function is going to be the separate of the work part into two pieces. Cut off unwanted portion of the part, or the cut of the outline of the flat surface. You can see that we have the power hacksaw, the band saw, and the circular saw. Other machining operation on the special geometries like the screw thread and the gear teeth cutting. The cutting of the screw thread, most methods do provide the producing of the external threads are the single point threading like the turning machine. The threading die, the manual one to generate that, the thread chasing using the self-opening thread dies, and we can do the thread milling. Method to produce internal threads are tapping using the solid tap and the collapsible tab, which is cutting teeth retract for a quick removal from the hole. So this will be the single point thread cutting, and the thread die is going to here. So that's what's happened. We're going to move the cutting tool to generate the shape of the teeth we would like to have. This one is using the CNC milling machine. In the old time, we used to have what we call the lead screw on any lathe machine. You can simply have the cutting tool, which is going to have the same profile of the teeth you would like to have, and the movement to generate that is going to be copying the lead screw thing. It's just below the lathe machine. You activate that by pulling the lever, and the cutting tool is going to copy the lead thread on the generated part. We can also do that using the milling operation, like this one. Okay, so what we're going to have once again is that is going to be a forming process, because the shape of the teeth we're going to have here is the same shape of the cutting tool teeth. And that's what we have once again if we'd like to have more diameter, bigger diameters on the work part. Principal operation for the machining of the gear teeth are the form milling, which is used a form milling cutter, the gear hopping process, the gear shaping, which is going to be either going to be a single point tool, or the cutter have general shape of the gear, but it's going to be cutting teeth on the one side. The gear approaching process for the internal and the external gears. So that's the form milling for the gear teeth on the milling machine. So we're going to have indexing movement for the work part, and actually the teeth we are going to have, the teeth shape is going to be decided by the cutting tool shape. So the form milling cutter has a teeth with the shape of the space between the teeth of the gear, and the gear plank is going to be indexed between each passes to establish the correct size of the gear tooth. It's something similar once again to the SolidWorks when you generate the pattern, the circle pattern, when you divide it into an equal divisions. It's not equal angles, it's equal divisions. So this division will represent the number of the teeth you are going to have on your gear. The gear hopping process. Now the cutting tool is a quite complicated shape. It's keep rotating while the work bar is going to be indexed movement. So while this one is going to be rotate, it's going to generate the gear shape teeth on the work part. So hop is a slide helix, and rotation is going to be coordinated with much slower rotation of the gear plank. Special milling machines called the hopping machines accomplish the relative speed and the feed motion between the cutter and the gear plank. The gear shaping process, actually we have the shape of the gear, but it's going to be the cutting tool. This one just keep going forward and backward like this process actually, until we're going to have the shape of the teeth on the cutting tool will be generated on the work part. So to start the process, cutter is going to gradually feed into the gear blank. It's not going to be in one cut, multiple cut. Each time is going to feed downward. The cutter and the blank are going to be slowly rotate after each stroke is going to maintain the tooth spacing, performed on a special machine which is called the gear shaper. And the gear approaching process, the same cutting tool we use in the approaching process actually is going to generate the shape of the gear on the work part. Now, actually, this is a shaping process. Okay, and you can see that both the cutting tool is going to rotate and the work part is also going to rotate, but in very slow motion. The cutting tool technology, we're going to talk now about the tool material we can use and the tool geometry we can have. We're also going to talk about the wear and the failure of the work part of the cutting tool, like the wear, the breakage, the chipping, and the deformation. So the types of the modes we have for the tool failures are the fracture failure. From the name, the cutting tool will fracture suddenly during the work. We have the temperature failure when the temperature is going to be too high for the tool material. So it's going to be softer and we're going to have some deformation. And we have the gradual wear. Continuous refraction, moderate temperature, and we're going to have the continuous wear for the work part until we're going to have the failure. For the cutting tool until we're going to have the failure. Now, between these three failures, which one you prefer? Consider that like your car tire, the gradual one. Because usually you can predict that before it's happened. Now this one, like you're driving your car, then the tire, boom. Or too high, and once again, the tire will fail. You don't know about how it's happened and why it's happened. But for the gradual wear, you can check the tire from time to time. Okay, it's weird. I'm going to change it. So usually we're going to talk about the gradual wear and how we can do the calculation for that. So the third mode is the gradual wear. The fracture temperature are premature failures. It's happened suddenly, and you don't want it to happen because safety, you are going to damage the work part, and also it will stop the operation of manufacturing during the time of manufacturing. So gradual wear is going to be preferred because it's going to lead to the longest possible use of the cutting tool. The gradual wear occurs on tool location on the cutting tool, which is the crater wear, the one at the top, and that's because we had the friction between the cutting tool and the chip. You remember this one? They can be decided by the rake angle. And we have the flank wear. This is the flank wear on the sides. From time to time, we're going to have some notch wear, which is going to be longer than the flank wear. So the relationship of the tool wear with a function of the cutting time we're going to have. So usually when I'm going to start using a fresh cutting tool, you're going to have some rapid initial wear at the beginning. It's a brand new, something like a car engine. When you start the engine for the first time, after you assemble it, you're going to have some rapid initial wear between the ring and the cylinder. Then you're going to have uniform wear during the steady state wear region. Suddenly, when the things became too old, start to have once again an accelerating wear rate until we're going to have the failure. So it's very important to run the operation through this period. Try to change the cutting tool before we reach this period. Because actually what's happening, if we're going to have the wear, that means the dimension of the cutting tool is going to be different, and this will give you an inaccuracy in the cutting process. Now for the velocity, higher velocity will simply going to generate less life for the cutting tool. So this is the time of the cutting we can have at 100 meter per minute velocity. Can go up to 40 minutes. In the case of the velocity is going to be 160, the life will reduce to 5 minutes only. And that's why we saw the video earlier for the velocity and the temperature. Okay, so this is the tool life with the cutting speed as we can have it as a log-to-log diagram. And from there, we can simply have the equation of the Frederick Taylor. The velocity multiplied by the time up to power n is equal to constant. So he did most of the tests on the machine and different cutting tool, and he found this equation. Higher cutting speed multiplied by the time up to power n, which is going to be different from one cutting tool material to another, will be equal to a constant which is different from one material to another. So n is the slope of this plot. C is the intercept on the speed axis at 1 minute of the tool life. The tool life criteria in the production: complete failure of the cutting edge, the visual inspection of the wear by the machine operators, and the fingernail test across the cutting edge, the change in the sound emitted from the operation, the chip becomes friendly and difficult to dispose, the degradations of the surface finishing, the increase of the power, the workpiece count, and the cumulative cutting time will be generated. If you are going to find these 9 criteria during you do your operation, this is a sign to change your cutting tool, because actually it has been reaching its last wear level. The tool material we can use, it should have toughness to avoid the fracture failure, because usually going to have an impact between the cutting tool and the work part. If it's not going to be tough, it's going to break up at the first contact. It should have very good hot hardness, because we know that the temperature is going to be increased. It should have good wear resistance, because we are going to have continuous wear for the cutting tool. For the hold hardness, depending on the material we are going to have, again, they have different hardness changes at higher temperature. So you remember the Rockwell test to check what the hardness of the material, the one which using the wedge penetrating in the part, and we can check what will be the hardness value. So typical hot hardness relationship for the selected material is showing in this diagram. The high-speed steel is the worst. The plain carbon steel is the worst. And the best one is the ceramic. Now, that's why we have a ceramic cutting tool nowadays. The high-speed is better than the plain carbon steel, which was the old form of the cutting tool we had. The silicon carbide and the ceramic are significantly harder at elevated temperatures. Now, for the history of that one, at the old times, well, let's say starting from the invention of the lathe machine, we always use the plain carbon steel as a cutting tool. During the World War II, they need to increase the production rate, so they found the high-speed steel. And starting from the 60s, because we had what they call the powder technology, now we start to have the symmetric carbides and the ceramic as a cutting tools. So the typical value of the N of the C in Taylor equation is going to be changed according to the material we are going to use. So you can see that for the high-speed steel, for non-steel work, I'm going to cut aluminum, for example, the value of the N is going to be 0.125, but the C value is going to be 120. That means that the life of the cutting tool is going to be longer if I'm going to use it on non-steel work. For the steel work, the value of the C will drop, and this means that the time life of my cutting tool will drop as well. For the ceramic, you can have the value of the N is equal to 0.6, but the C value will go up to 3,000. Cemented carbide is 900 by 500. So you'll say, okay, I'm going to use the ceramic to do all the works. That's wrong, because the ceramic cannot do a high depth of cut in its cut. That means you are going to increase the number of the passes. So still, the cemented carbide is the best option you can have during the cutting operation. So the high-speed steel is highly alloyed steel, capable of maintaining hardness at elevated temperature better than the high carbon and low alloy steel. The high-speed steel composition are the tungsten and molybdenums. We can use the chromium and vanadium. The carbon, of course, going to be added. The cobalt in some grades. The cemented carbide is class of the hard tool material based on the tungsten carbide as the base material. And sometimes we also going to add some cobalt as a binder. Now, once again, what's happening in the powder technology, for example, for the cemented carbide, you are going to change the material into a powder form, melt it, and expose a very high speed air on it, so you will take the particles away. So again, to make it smaller, something like the powder, you have to compact it at high temperature, then center in the thing. Without binders, which fill the cavities between the particles, it's going to still brittle. So in this case, we're going to add the cobalt, which is going to be melt faster than the carbide itself, fill all the cavities, solidify, so it's going to work as a binder for the carbide insert. Two basic types, the non-steel cutting grades, which only with the cobalt and the carbide, and we can simply add the titanium or the titanium, I think, for the steel cutting grades. We also can use the coated carbides. So the carbides in the middle, we can coat it for the surface hardening, the process we learned earlier. Okay, and this is similar to carbide insert coated with one or more layers of the titanium and the titaniums, and or with the aluminum oxide on or other materials. Coat thickness is always going to be something between 2.5 to 13 micromillimeters. So we're only going to increase the surface toughness, but the bottom will remain the same. The cermet is a combination of the TIC and the TIN and titanium carbonitrate, the TICN, with a nickel or the molybdenums as the binders. And I think I should show something here. The application is going to be very high speed finishing and semi-finishing of the steel, stainless steel, and the cast iron. So make it hard, it doesn't mean always going to be good for the cutting. This one is very hard, but only going to be used for the surface finishing because it cannot take the impact of high depth cut. For the ceramic, okay, it's a fine grade Al2O3 pressed and centered at higher pressure and temperature into insert with no binders. The application is high speed turning of the cast iron and steel, not recommended for the heavy interrupted cuts like the rough milling. It's good for the due to the low toughness we have there. It's widely used as a pressure for the grinding process. The synthetic diamonds, well, it's look like a diamond. So synthetic polycrystalline diamonds, it's actually we took the powder, we compress it with the binders to have the polycrystalline diamond, the SPD. Fabricated by the synthetic of the fine-grained diamonds crystals under the high temperature and the pressure in the desired shape with little or no binders. Usually applied as a coating of 0.5 millimeter thickness of the carbide insert. The application is the high-speed machining of the non-ferrous metals and the abrasive non-metals such as the fiberglass, reinforced polymers, graphite, and the wood. Not for the steel cutting. So it's considered to be one of the hardest material you can have as a cutting tool. The cubic boron nitride is next to the diamonds. Cubic boron nitride is the hardest material known after the diamond. Fabrication into the cutting tool insert same as the SPD. Coatings can be used on the carbide insert. It's going to be better than use it as a separate cutting tool. The application in machining is steel and the nickel-based alloys. The problem is that both types are too expensive. The tool geometry, we said once again, we can either have as a single point tool in the turning, boring, shaping, and the planning, or we can use it as a multiple cutting edge tools like the drilling, reaming, tapping, milling, broaching, and the sewing. The single point geometry have 7 elements of the single point geometry, as you can see here. We have the cutting edge angle. We can have the side cutting edge angle, the nose radius NR. We have the side rake angle. We have the side relief angle, the back rake angle, and the end relief angle. So why are we doing that? Why we have all these angles? Why we designed this way? Why we have 7 elements to make one single edge cutting tool? Can you see the shape? We try to reduce the area as much as possible. That's mean again to have more forces, more pressure with less forces, more pressure on the area with less forces. We do this design to reduce your force and reduce your power. So holding the single point tools can be as following. We are going to have the solid tool shank. So it's going to be made of the usually the high speed steel. So I can do the cutting on this side by the grinding process to generate the shape by making all these 7 elements at this point. And that's the old type of the cutting tools. We used to have someone to called the tool maker. He take the cutting tool from time to time, sharpen it, and bring it back to you. So this is a solid shank tool, typically of the high-speed steel. Now the other type, the brace cemented carbide insert. So the shank can be made of the fiber carbon or the high-speed steel. But actually, we're not going to use it to cut. We're going to insert the brace to the tool shank. We're just going to hold it by using certain type of the super glue, and it's going to do the cut by itself. If I'm going to have this one need to be changed, I have to take it out, put a new one. But you cannot do it on the workshop. You have to send it once again to the tool maker to change it for you. But we still have the alternative one, the mechanically clamped insert. So just unscrew that, change the carbide insert with a new one, or turn it. Because most of the carbide insert have 4 cutting edges, or 3, or 2. So these are the common insert shapes, as you can see in front of you. Different angles, different number of the cutting edges. Okay, so that's what we are going to have for each different design. If I'm going to have it long, the small angle, what will be the use? Versatility and the accessibility. I can do a long depth deeper cutting by using a longer cutting tool. Okay, if I'm going to go to this side, I'm going to increase the angle and increase the number of these sides, of course. I'm going to have more strength, less power requirement, and the variation tendency. Sorry, higher power requirements and the vibration tendency will increase in this direction, but it's going to reduce on the other direction. The twisted drill is multiple cutting edge, most common cutting tool for the hole making, usually made of the high-speed steel till today, but we still can use the carbide insert drilling tip, and that's what we're going to talk about later. So this one is actually using the carbide insert, as you can see here. Twister operation, we are going to have rotation, and we are going to have the feeding of drill bit result a relative motion between the cutting edges and the work material to form the chip. The cutting speed varies along the cutting edges as a function of the distance from the axis of the rotation, and the relative velocity of the drill bit is going to be always 0. That's what at here. The velocity is going to be 0. As long as we are going to go further, the velocity is going to increase because the radius of movement is going to increase. And instead, large thrust force is going to be required to drive the drill forward into the hole because the velocity at the tip we said is going to be 0, so we almost having no cut. So how we can replace that? Add more thrust force to penetrate it, then we're going to have the cutting to be started. So the problem we are going to have usually in the drill operation is the chip removal. And that's why we have to design the flutes to provide self-cleaning for the hole. So the flutes must provide sufficient clearance that allow the chip to remove from the bottom hole during the cutting process. The other problem we can have is the friction going to make the things worse. I mean the chip removal process. So the rubbing between the outside diameter of the drill bit and the newly formed hole and delivery of the cutting fluid to the drilling point to reduce the friction and the heat is going to be difficult because the chips are moving in the opposite direction. Again, to put the cooling fluid on one direction, the chip tries to go outside from the same direction, and this will be a big problem for you. So simply we can use what we call the gunner drill. We're going to talk about this one now. But first, let's go to the alternative drill to prevent this problem, which we call the straight flute. So you can see that this will be the cutting area on these sides, and this flute is going to be too big to release the chip from there instead of having the screw fluid. So a straight fluid drill using the indexable cemented carbide insert for a higher cutting speed. The other one is called the gun drill. We call it gun because simply we have a hole inside the drill tip. It's going to send the fluid from this side. So actually the direction of the fluid sending is going to be the same direction of the chip exit. So for deep holes, it has a carbide cutting edge as well, single straight fluid and coolant hole running through the entire length. The other one is what we call the spaded drill, like this one. So for large diameter holes up to 152 millimeters. Now once again, again to have very big area for the chips to be released. The milling cutters, now we are going to have multiple teeth in this case. This will be the plain milling cutters, two geometry elements of 18-tooth plain cutting cutter you can have on this side. The face milling cutters, two geometry elements of the 4-tooth, and it can be more of course. Face milling cutters, this will be the side view and this will be the top view. So each one is going to remove its portion and we can simply calculate what will be the feed per teeth as we mentioned earlier. This will be the end milling cutters. Okay, look like the drill bit, but designed for primary cutting with its peripheral teeth. It's not going to be cut from the center as we had in the drill bit. The application is for the face milling, profile milling, and the pocketing because it can cut from the side edge as well, from here as well. And cutting the slots, the engraving, the surface contouring, and the die sinking. The cutting fluid we can use a liquid or gas applied directly to the machining operation to improve the cutting performance. That's the definition of the cooling fluid in the machining operation. So how we can simply improve the cutting performance? It's called the cutting fluid, but actually it's going to do two processes, cooling and lubrication. So two main problems addressed by the cutting fluids, the heat generation at the shear and the friction zones, and the friction at the tool chip and the tool work interface. Okay, so these are the two main problems addressed by the cutting fluid. Reduce the heat generation and reduce your friction. The other function and benefits are wash away the chips as we saw in the case of the drilling operation. Reduce the temperature of the work part for the easier handling. Improve the dimensional stability of the work part because we are going to cool it down, it's not going to be expanded. The classification are coolant or lubricant. So the cooling fluid can be classified according to the function like coolant designed to reduce the effect of the heat on the machining, but it cannot do any lubricant. Sometimes I saw actually this application, they were using the water, just water as a cooling fluid, as cutting fluid. That's wrong because actually if you are going to work on steel, you are going to have rust at the end. The lubricant designed to reduce the tool chip and the tool work friction. And once again, I saw some people using the oil, just the car engine oil, as a lubricant, but it's not going to work as an efficient coolant. So the coolant is a water used as a base in the coolant type of the cutting fluid, most effective at high cutting speed, where the heat generation and the high temperature are going to be the main problem. The most efficient on the tool material that are most successful by the temperature failure like the high-speed steel. The lubricant usually is going to use the oil-based fluid, most efficient to at lower cutting speeds, also reduce the temperature in the operation, but at lower rate than the coolant cutting fluids. The problem we have with the cutting fluid is the contamination. Okay, we are going to have oils, you're going to have increasing in temperature, reducing in temperature, rusting problems. So, for example, the contamination we can have is drum oil from the machine itself, the garbage, like the cigarette butts, because you don't expect that every factory is clean. And small chips, the fine one that you cannot filter, And we also may have some mold, fungus, and bacteria, especially if it's going to be a water-based. So dealing with the cutting fluid contamination is very hard, but to improve that, you have to replace the cutting fluid at regular and frequent intervals. Don't leave it for a long time, and this will reduce the mold, fungus, and bacteria appearance. Use the filtration system to continuously or periodically clean the fluids, and we can use the dry machining in very narrow applications. Now, what's the dry machining? We are going to do the cut with no cutting fluid going to be used. Avoid the problems of the cutting fluid contamination, disposable, and the filtration. The problem we have with the dry machining is the overheating of the tool. Operating at lower cutting speed and production rate to prolong the tool life, and this will make the longer production time and this disadvantage. The absence of the chip removal benefit of the cutting fluids in the grinding and the milling process. But we still can use it. Now, if you're going to cut, for example, the brass, usually they do it as dry cutting. That's it for today. So I promised you to show a video for something. What was the video for? I don't remember. Anyway, so